right, lesson 28. It's going to be kind of a shorter one, but you guys are going to have calculations that you need to finish up on your own before you submit these notes Saturday by midnight. And so you're going to have to use information from the previous lecture to fill this in, which you should have already calculated these. And if you haven't, you're going to have to now. So now we are going to calculate the entropy change of the universe, which is our third. So we have the entropy of the system, which we do with the values in the table, products minus reactants. Then we have the entropy of the system, and then we have the entropy of the surroundings, which we're going to calculate with the enthalpy of the system divided by the temperature. And now we're going to add all those things up and calculate the entropy of the universe. Okay, so using the answers from the previous two problems, 3 and 4, we're going to calculate the entropy of the universe for the following. So the one we did together was A. Sorry, there's something gross on my iPad. Was A. And so what we're looking at is entropy of the universe is equal to the entropy of the system or the reaction plus the entropy of the surroundings. So if I go back to my last lecture, my entropy that I calculated of the system was negative 166 joules per Kelvin. And I'm going to add that to my surroundings, which now you can see why it was important to go ahead and convert the value to joules, because I'm going to be adding them together. So if I had not done the conversion before, like at the end of the last problem, I would have had to do that now. And either way is fine. Just make sure you do convert. And the answer we get is 1987, which oddly enough is the year I was born. So when I see this, I want to say 1987 like it's a year. But it's 1,987 joules per Kelvin. So if we look up at our options up here, the delta S of the universe is greater than 0, which suggests that this is a spontaneous process. Okay, so if delta S was less, this would be non-spontaneous. Okay, so go ahead and do that for the last 3 that you did on the previous lecture, and then go ahead and take it a step further and tell me if this process is one of the following: spontaneous, non-spontaneous, or equilibrium. So this is what quiz, gotta make sure I get this all correct in my mind. I've got my calendar right here. Quiz 9. Yeah, this will be, shoot, I should have told y'all before. Anyways, I'll make an announcement to make sure. Quiz 9 is going to be over lesson 26 and 27. Okay. Quiz 10, which is coming up, will be over lesson 28 and 29. Okay. So I'll put that in an announcement in your weekly to-do list as well. Okay, but if you're listening ahead, you may get to this before the weekly announcement comes out. So, third and final law. The entropy of a perfect crystalline substance is 0 at the absolute 0 of temperature. Okay, and so the reason why is, if we think about what absolute 0 means, I think that Cameron or Levi answered this at the very beginning of the year, or last year when we discussed this at the beginning of the class, that when we're at a temperature of 0 Kelvin, this is where all molecular motion stops. Therefore, because molecular motion stops, if you think about solid liquid gas relationship, this means that the entropy would also be equal to 0 because there's no molecular motion, and we know that entropy increases as we increase molecular motion. All right. Although we can never get to absolute 0, and thus we'll never have an absolute entropy of 0, the relationship that we assume we have allows us to calculate what we call true entropies. True entropies. So these are, okay, it's a long story, but there used to be a professor here called Dr. Butterworth who taught Gen Chem before I did, and she came up with this list of, or she was taught this list of simplified rules that she learned from a professor in her undergrad because she was what we call a physical chemist, and physical chemistry is based on things like thermodynamics. So there's a whole branch of chemistry just focused on thermodynamics and quantum mechanics, things we learned last semester. And so she says, a comedian once simplified the laws of thermodynamics by likening life to a game. Okay, so if the first law is energy can neither be created nor destroyed, the first rule of the game is you can't win. The second law says the entropy for a spontaneous process is always increasing. You'll never break even in life. The third law is that entropy of a perfect crystal at absolute 0 is 0, and that means you can't quit the game. Okay, so it kind of to me sounds like Jumanji, if anything, but if you laugh at these, you're probably secretly a theoretical chemist in your heart of hearts, because I read this and I don't necessarily chuckle out loud, but she always did. And so if you want to know more about theoretical chemistry, physical chemistry, graduate school may be your calling. But for me, I just like to know the definitions that we are given in the book because I understand those better. So this ends lesson 28, and this should finish up this week, and we'll pick up with lesson 29 after the weekend, okay, which is also coming into Easter break.